our discussion was we discussed the entropy cost for number 1 and number 2. So when x is in here and when y is in here. And so the final thing that we have to consider is when z is in here. So that's what we are doing. Are we okay? Do we still remember the discussion? Okay. Where do I want to write it down? Okay, so maybe I can erase this part. Okay, so finally, when z is in F, again, we want to use the entropy approach, and when z is here, we have to open the palette of its neighborhood, right? Because we don't know whether the neighborhood is good or bad, so we'll use the neighborhood approach. So in this case, again, this T of z is at most 1 over d times the entropy of F of the palette of the neighborhood of G plus 1 over d entropy of F of the neighborhood of Z given the palette and entropy of Fz given the neighborhood. Like this. Okay, so are we okay with that expression? Okay, then what can we do? So again, this palette, this costs big O of 1 over d, and this can be problematic. So in some delicate question, this extra cost really caused the crucial problem. But at least for our special case, that one is okay because we will find even bigger penalty from the vertices in F. So for example, what can we do with this expression? Here, let's copy what we did in this analysis. So again, let's assume that Q is 4 and see what happens. So when Q is 4, from this argument, we saw that unless we equipartition the color, if we have this unbalanced color distribution, then always the entropy is significantly smaller than the maximum value. We saw that, right? And then I claim that if we have f of z and f of the neighborhood of z, and when Q is 4, two color, this is impossible. This is my claim. And if this claim is true, then we have that this one is at most 2 times log Q over 2 minus some constant vector. Because we always have some imbalance in our color partition, and that gives us the constant fraction of the constant big penalty, the constant penalty. Again, for now, let's just assume that we only have 4 colors. And in this case, why is it impossible to have 2 colors for this and 2 colors for that? Hint, Z is in F. And we have this picture. Yeah, there must be a flaw here, so it must be bad. Why? We have to use the property of the container. Why? Great, yes. Because F is contained in the neighborhood of X. So that means for each vertex in F, there must be an element in X, which is bad. So there must be a bad vertex in the neighborhood of Z. Does anybody there? Do we agree that there must be a bad vertex in the neighborhood of Z? Because Z is contained in F, which is contained in the neighborhood of the flaw set. So by the definition of the neighborhood, there must be a bad vertex, which is inside the neighborhood of Z. On the other hand, this Z is good. And because we have one bad vertex and one good vertex, they have a conflict. So that means as soon as we have a bad vertex in the neighborhood, this one loses its choice. So we cannot really have 2. And the next possible case is when this one has one color choice, and this one has 3 color choices. And we already know that if this happens, then the entropy is much smaller than the maximum possible. Okay? So you worked on this question, and did you see that if we have unbalanced palette, then the entropy is far from its maximum? Did you check that? I hope you checked. Would you like me to check this computation? I hope not. Okay. So this is what we have. So we are almost done. So from number 1, we have this benchmark. From number 2, we have something slightly bigger than the benchmark. From number 3, we have big O 1 over D, and then we have this. So we have this bigger, much bigger penalty. And we're going to leverage this penalty in summing the entropy of the entire thing. So let's do the computation. I'll just erase this board. OK, so if we combine number 1 and number 2 and number 3, so this is entropy of F. No, this is at most entropy of F. And if you combine all of them, then we have this is at most n times log Q over 2 plus big O Q 1 over D times the size of the neighborhood of S minus big omega Q, so big omega of 1 times the size of F. Do you agree with this? Because we have big omega 1 term from here and over there, so that it comes from all of the neighborhood of S. And then we have this penalty for the vertices in F. So we have this. Okay, and we want to say that this is smaller. So this was our goal, is to show that this is smaller than n log Q over 2 minus something large. And that large thing, to say that, we have to show that this thing, what can I say? So the last thing is this. So we are done. If the size of the neighborhood is much smaller than D times F, then this one will be dominated by this thing. So we are going to have this as a conclusion. So we are done. So the final step, but are we OK so far? OK, then the final step, why do we have this? How can we show this? And this uses the properties of the containers. So it's not just given for granted, but we have to use these degree properties of the containers. So number 1, okay, part A. So I'll just sketch this because you have already done this. We saw last time that the size of F is almost bigger than S. So up to some minor term. You proved this in the problem session yesterday. So we have this. So that, and then the second part is the neighborhood of S is bounded above by, I'll write down the answer and then I'll ask you why. This is at most this plus liter of D times this. So part A is already done yesterday. Part B is the question that I'm asking you. But if we combine part A and part B, then this gives this. Do we agree with that? Because this one is at most F plus liter of D times F. So this is much smaller than D times F. OK, then my question, why do we have B? So
the number of neighbors outside F should be very small, like liter of D?
Yes, great. OK, great. So we just look at the edges coming from here to outside of F. And we already said that this escaping edges is smaller than psi, which was liter of D. Good. So here I said for all of the vertices in S, dF is close to D. That means the number of escaping edges is liter of D. So that gives an upper bound on this part. So this neighborhood is the size of F plus the number of escaping edges, which is this. OK, so we are done. Any questions? So this takes care of the very special case of the coloring problem. But again, finally, let me emphasize that, again, the real issue is when we have some flaws on the other side. And in this case, what complicates the problem is we do not have this argument anymore. So this argument really crucially uses the fact that Z is good. But if we do not have that assumption, then we have to do something much involved. So that is the real issue, but I don't think we can handle that. We can discuss that in this lecture. So this is the end of the coloring. We are not done yet. So as the next step, we'll prove the first container lemma. Unfortunately, the next thing that we discuss will be a bit technical, because I want to give you the complete proof for the first container lemma. So by the nature of this proof, I cannot avoid the technicality, and I'll try to explain this as much as I can. So we prove the first container lemma, and don't worry if you don't remember this. I'll give you the definition and statement. So the definition, G, AG, this was the set of A, where A is two linked. And the closure of A had size A. And the neighborhood of A had size G. And here, the important parameter is G minus A, the expansion. And we give a name for this. We use T for the expansion. And then the definition is the psi approximation. And in my notes, I have the full description of the properties. But let me just replace the rigorous definition by the picture of the approximation. So we have this, the closure of A. I think I should say A now. Closure of A. And then we have its neighborhood. And we have a pair of S and F. So this is S. I think this picture was just here. And then I erased it. And this is F. And S has a large degree in F. So dF is bigger than d minus psi. And if you look at outside of F, this is ds is smaller than psi. So this is the definition for a psi approximation of A. So can I skip the rigorous definition? OK. And then here, so I used psi, but you can think psi is about d to d 2/3. Of course, we have much more flexibility in reality, but for this exposition, let's assume that. And then the first, the statement of the first container lemma is basically this. The number of containers is not so large. So there is a family U, which has parameters A and G in 2 to the O. So this is a pair of sets. So a subset of O and a subset of E with the size bounded above by n/2 times 2 to the big O of G log D over psi, such that every A in GAG has a psi approximation SF in U. Okay, so it's a long sentence, but basically it says that the number of containers is at most this quantity. Okay, and then so now we prove this, and we construct the containers in 2 steps. And when we do this, in particular in the second step, the property that we crucially use is this. There are no edges between the closure of A and the neighborhood of A. So it looks similar to independent sets. Yes? Thank you, TA. Great. So is this believable now? Is more believable now? Okay, so there are no edges between A and its complement, the complement of the neighborhood of A. And this looks pretty similar to independent set, because an independent set that means there are no edges inside the set. But instead of having that assumption, we have used this assumption that there are no edges between A and the complement of its neighborhood. And this property is always true for any graphs. Okay, step one. This is some crude approximation using some classic results. And this is a simplified version. This is not equal to original, because in the original version, Sapozhenko used more what can I say, more dedicated, I don't know if that's the right word, so more involved argument for the first step, because in his assumption, the expansion was much weaker. So his argument works for the expansion like 1 plus something like O tilde of 1 over d squared. So his argument works the expansion as small as this, but in our case, we are assuming that our graph is a Hamming cube, so we have the expansion like big omega of 1 over root d. So so in this bigger expansion, we do not need the original argument of Sapozhenko, and for the educational purpose, I'll just replace his argument by more classic results. That's what's happening here. And so what is this crude approximation? This is called a cover. So for any A in O, we say B covers A if it looks like this. This is the closure of A, and then B is here. And the property is the neighborhood of B contains the closure of A, and the neighborhood of the closure of A contains B. So this is a definition for a cover. And let me not write down this in a sentence. Is that okay? Okay, this is the definition of a cover. And then my claim, again, this is pretty well-known result. My claim is that for every A in G, there exists a small cover. So there exists a cover B of A of size. Can you see here? Is this too low? Is this okay? Of size big O of G log D over D. Have you seen this before? This is pretty classic. Have you seen this result before? No? Okay, then I think this is good to know. So and this does not require A to be too late also. So it just requires the size of the size of the neighborhood of A to be G. In that case, you can find a cover of size this. And compared to the size of the neighborhood, this cover is very, very small. And then why do we want to have a small set? Because small sets are cheap. Okay? That's the reason why we want to approximate the given set using some set of a small size, because they are cheap to specify. So instead of using the full information about the neighborhood, we just use the information about the cover of the set A. Okay, and I will not prove this claim in full, but the proof is pretty cute. Proof, probabilistic. Do you mean what this means? This means just pick vertices in the neighborhood with a certain probability and show that that is a cover. What I said is a lie. We cannot do that. So what we do is to choose a random subset. So I'll just say it. I will not write it down. And some detail is written in the notes, but not in full. So in this neighborhood, pick a random subset of the neighborhood with probability log D over D. Then with a good probability, or in average, this random set will cover most of the vertices in A, or in the closure of A. And then what you do is, for these small leftovers, just pick any matching like this to cover this vertex and combine them. And then that's the end of the proof. So this is pretty simple, so let me not prove it. Just remember, the keyword is pick vertices at random. Okay? Are we happy? Okay, so let me move on. And once we have this, now we can say that the cost for this cover is very cheap, and the reason for that is because the size of the cover is very small. So that is my next claim. I don't have space. What can I do? Maybe for this one, all that we need to remember is this, right? We just want to show that the size of the containers, the number of containers is small, so let me erase the rest. And I will keep this. And then the next claim is that So let me give a name for the covers. I will use B for the collection of covers of A from that construction. Okay, we just collect all of the covers of the sets in GAG and check. Ignore this line. Check that for every B in B, B is 4-linked. And this is because A is 2-linked. I hope this is believable because here A is 2-linked and B has this close connection to A, so you can easily show that if A is 2-linked, then B is 4-linked. And let me leave this to you. I will not prove this. Oh, by the way, do we know the definition of 4-linked? This means QD to the 4th induced by B is connected. Again, so this just means B is more like nearby. It's not far from each other. It's more like nearby vertices. And based on this, we claim that the size of the collection B is at most n/2 times 2 to the, let me erase this, 2 to the big O of G log square D over D. So if you are not happy with this technical looking quantification, then don't worry about that. It just says that the cost for the cover is very small compared to our benchmark. What is our benchmark? Our benchmark is here. But compared to this, because this psi is about D to the 2/3, so this cost is negligible compared to our benchmark. That's all that it says. So if you are not happy with this, then just forget about it. All that it says is the cost for the cover is negligible. Do you see why we have this bound? Why? I saw many of you are working on this question in the problem session. So why is this true? In the problem session, how many questions did we have? In the last problem session, how many questions did we have? Two, number 1 and number 2. Do you think this is number 1 or number 2? Does this look like entropy? What does this look like? It's bounding the number of connected sets. And that's the reason why we need this. B is 4-linked. That means B is connected in Q to the 4, whose degree is D to the 4. So we can just apply the lemma that you just proved. I hope you proved it. That you just proved to show this claim, and then we are done. Are we okay? So I will just say this is done, and this is done by you, probably. Okay? So I will skip this. So So this is the end of part 1. So I said we'll prove this container argument using 2 steps. And the first step is to construct these covers. And second step is to push this cover to refine this cover to get this container. That's what we do. So are you happy so far? So we constructed a cover whose definition is here, and the cost for the cover is negligible. So now I will just erase the entire board, the second and the third board. And for the container argument, I will write down the entire algorithm. And let me erase this. So can you remember this? You try to remember it. I'll give you 3 seconds. OK, so you remembered it? Then I will erase it. And here comes the algorithm. So this is step 2. So first, as usual, we fix on ordering on the vertex set of QD. And this is because when we implemented the algorithm, we want to remove the ambiguity. So we always want to have a unique choice for the vertices. So we fix on ordering. And the input for this algorithm is a member A in the collection GAG and its cover B. So if we input A and B to this algorithm, and what happens in this algorithm is this. So we start from the closure, sorry, A or the closure, they're the same thing. I mean, A not the same thing. A determines the closure of A, and its cover B. This is the beginning, and this algorithm consists of 2 phases. In the first phase, we construct something like F, but this is not exactly F, so we'll call this F prime. And the way to do this is to grow B, and in this, while we grow B, we'll try to keep this dF condition. And then once we have this F prime, it gives some version of S prime, but this S prime is too big. So in phase 2, what we do is to trim S prime. So we'll make it smaller and smaller, and then in doing so, we'll try to maintain, or we'll try to achieve this ds property. So at the end of the day, we'll have a pair of S and F that satisfies dF condition and ds condition, and it will be done in two phases. So this doesn't exist in the first phase. So and then let me tell you what that algorithm is. So in phase 1, so picture we start with is this. We have B, and we have the closure of A. Oh, sorry, we have A, and we have this. Sorry, we have A, not closure of A. The input is A and B. So in phase 1, we grow F prime, and the goal of this phase is we want to achieve the dF condition. So first, we set B, our cover, to be our initial F prime. And then we keep growing this F prime in the following way. If there exists U in the closure of A, such that if this violates the dF condition, which means dF prime U, maybe it's better to write it this way, the neighborhood of A minus F prime U is bigger than psi, then just update F prime by F prime union the neighborhood of U. course, there can be multiple U that does this. And if that happens, then what can we do to keep the uniqueness? We just use the ordering to pick the first one. That's how we break tie, okay? And then we repeat this until there doesn't exist such U. So can you picture this? I think it's better for you, for yourself to picture this rather than I keep saying it. So but roughly what happens is we start from this B, and each time we grow this B until there's nobody who breaks this DF condition. So if there is somebody in the closure of A that breaks this DF condition, that means if this one has too many neighbors outside of B or the current F prime, then just add this to B to grow, and then grow, so redefine B to be this bigger set. Okay? And so if you're familiar with this kind of algorithm, then probably you see why we need this lower bound. This is because by having this lower bound on the neighborhood, we can give an upper bound on the number of iterations that happens in the first phase. Because here, every time we add psi many vertices to F, that means this iteration cannot exceed some number of iterations. Because eventually, this set F prime cannot exceed the neighborhood of A. So that's the reason why we need this lower bound. Again, this is to upper bound the number of iterations. Because, again, all of the vertices that we add belongs to the neighborhood of A, because this vertex U is chosen from the closure of A. So we cannot go forever. Eventually, it will stop. Okay? That's the reason why we have this lower bound. And after this phase 1, do you believe that we have this DF condition for the current set F prime with this, the closure of A? So this is the end of the first phase. I will keep this one so you can think about this. And let me move on to the second phase. In the second phase, as I said, we shrink S prime. And while doing this, our goal is to achieve the DS condition. So this is an algorithm, so we need something to start with. So we set the initial S prime to be the collection of all of the odd vertices, such that dF prime U is at least D minus psi. So in this algorithm, we implemented this algorithm for the vertices in the closure of A, but eventually in our implementation, we will not see this closure of A, so we just collect all of the vertices whose degree to F prime is big. So this collection observes the DF condition. And this, of course, contains, is contained in the closure of A. Is this right? Oh, yeah. Contains the closure of A. And at the end of this algorithm, the first phase will output F prime, and that F prime determines S prime. This is an important part because once we have an F prime, we do not have any extra cost for S prime, at least at the initial step. And then now now S prime is given for free, and then we do some algorithm to shrink S prime and then achieve the DS condition. And let me show you what that is. So what happens is if there exists some W in E minus the neighborhood of A, that violate the DS condition, so DS prime is bigger than psi, then update the S prime by S prime minus the neighborhood of W. And we repeat until there is no such W. Again, just think about what it does, because I think that should be much better than I explain what it is. So just try to convince yourself that that should be much better. But anyway, so what happens here is, so in the initial setting, when you look at F prime and S prime, we know that this S prime satisfies or achieves or satisfies the F condition, which means everybody in S prime has a large degree in F prime. This is because of this, our definition of S prime. But we aim for the DS condition, which means whenever we have a vertex outside F prime, if you look at its degree to S prime, we want this to be small. But that is not guaranteed from the initial setting of S prime. So what we do here is whenever we have some vertex outside of the neighborhood of A that violates the S condition, then we just get rid of those guys, kick out those vertices, and we keep shrinking S prime. And because this vertex is chosen outside of the neighborhood of A, those vertices are outside of the closure of A. So we still maintain that the evolving set S prime contains the neighborhood of A. So again, what we do is to make the degree condition satisfied, while F prime is contained in the neighborhood of A, and S prime contains the closure of A. Okay, and the last step, finally, we output. So this is the final thing. We output S. This is just S prime. And F, I'll write it down, and you can see why we need this. If we just say F is F prime, then this can be problematic. And we have to add some other vertices, some other even vertices, such that DSW doesn't violate the DS condition. Because in the implementation of this algorithm, we only touched the vertices outside of the neighborhood. So there can be some vertices in the other side. What can I say? And this one is still contained in the neighborhood of A. Okay, so again, not again, let me try to straighten this up. So in this algorithm, we only touched the vertices outside of the neighborhood. So we didn't touch the vertices inside the neighborhood of A. So we need to treat the vertices who can be possibly in the neighborhood of A to make the DS condition to be satisfied. And you can convince yourself that this set is actually contained in the neighborhood of A. Okay. This is it. This is the end of the algorithm. So what's left is just to show that the cost for this algorithm is not bigger than our benchmark, which you remember. Okay, so let me leave it as an exercise. So the entire algorithm is written in my lecture notes, so you can check that. And one easy exercise is, where can I write it? Easy exercise is to find the space to write it down. So let me write it down here. So an easy exercise is that this output, SF, this is a psi approximation of the input A. But the final part is the number of outputs of this algorithm is what we expect. Do I want to erase this? No. I don't want to erase the algorithm. So let me keep this picture. And my claim, the number of outputs where we run this algorithm for all of the A in G, AG, such that B covers A. This is 2 to the big O of G log D over psi. And then this will finish our proof. Oh, I think I'm in trouble. I still have one more page, but can I finish this in 10 minutes while not erasing those two boards? I really have no idea. What can I do? If I write it too small, then you will complain. And if I don't write it, then you will complain. Maybe I can just finish this lecture now, then you will not complain. Okay, let me try. Okay, so the cost, maybe how about doing this? So I'll just prove the cost for phase 1. But the entire proof is written in the notes. But the proof for phase 2 is very similar to the proof of phase 1. So can I erase that board and just discuss phase 1 and leave phase 2 to you? Is that okay? So everybody's happy. Okay, great. Okay, so proof cost for phase 1 is this. Okay, so observe that the final f prime from this phase 1, this is determined by the use that we pick. Do we agree with this? So in this algorithm, we start from the cover, which is given, which is our input. And the way that we grow this f prime is to pick some vertex in the closure of A and add its neighborhood to f prime. So that means the entire f prime is determined by the vertices that we pick, because we already know the input B. Do we agree with this? So that means to specify f prime, we just need to specify the vertices that we add. And we already discussed that the number of such vertices is small because we pick the vertices with a high degree. Okay, so let me write it down. The number of vertices that we pick, this cannot exceed G over psi. And we already discussed this. This is because G is the size of the neighborhood of A. And each time we add psi many vertices to the neighborhood, so to f prime, and because f prime cannot exceed the neighborhood, so the number of vertices that we pick cannot exceed the size of the neighborhood divided by psi. Okay? And this is pretty small. Very small number of vertices, so they are cheap. Okay? And then, so we specify those vertices, like G over psi vertices, from somewhere. This is what we discussed yesterday. If we specify some vertices from the entire universe, this is too expensive. So we have to shrink the universe from which we find our sets. So that's the trick here. And where can we specify those vertices? I claim that those all lives in the neighborhood of B. So in this specification cost, we do not see A and the neighborhood. We only see B. And from there, we want to specify, so we want to, so only with that information, we want to specify the vertices that we add to this algorithm. And this is pretty obvious, is it right? Because B, the neighborhood of B covers the closure of A. And in this algorithm, we only pick the vertices from the closure of A. So this specification cost cannot exceed the number of sets of size this, of number of subsets of this set of size this. So this cost is at most the size of the neighborhood of B choose G over psi, which is the neighborhood of B cannot exceed D times G because B lives inside the neighborhood of A. So B cannot exceed G, and because this is a D regular graph, so the neighborhood of B cannot exceed D times G, and then G over psi. So this is at most 2 to the big O of G log D over psi. This is the end of the proof for the cost of the first phase. Any questions? I will leave you some time to digest this. So again, this algorithm runs for all of A and given B. Oh, so all of A such that B covers A. So our input is A and B, and then it outputs something, and then this just gives a naive, not naive, this just gives a loose, not loose, but upper bound, on upper bound for the number of outputs from this phase one. And is this the same as what you still remember? Question?
Can you make the DG like G log?
Of course, yeah, you can do that. Yeah, but that doesn't change anything. Yeah, great. But that's a great question. Of course, yeah. We know much better about the size of the neighborhood of B. Of course, yeah. Good. Any other questions? Okay, then are we happy with finishing the lecture now? So please check the cost for phase two is written in the notes. Okay, then yeah, enjoy your weekend.